Okay, folks, let's get into the properties of first order reactions. Okay, so now this looks very similar to what we said with zero order reactions, just some simple A goes to products. However, now in a first order reaction, as we might guess, there is a dependence of concentration on the rate of the reaction. And so the way that we would set that up would be the following. We're going to say negative dA by dt, just getting the relative rate written down there with the correct stoichiometric coefficient. And now that's going to be K times A. And because we know this is a first order reaction, that's A to the first power. So I don't have to write a 1 right there, right, mathematically speaking, but I did just so we're clear that that is to the first power. Okay, so similarly, I can rearrange this algebraically as is standard to do by putting the negative sign over on this side times A. And now our goal is to solve this equation. And what I want to point out here, this is our first example of a differential equation. Okay, and so the functional form of that differential equation is dy by dx equals negative k times y. So what we want to do is keep the y's with the y's, and in this case the x, which is time, is going to go with the k. So this is what we would call a simple, I'm going to write diffie q for differential equation. Okay, so now working from this version right here, we're going to end up with dA divided by A equals negative k dt. And now our goal is to integrate both sides from some initial condition to some final condition. And what we end up with is the following. So recall, when we integrate dA over A from some initial to some final condition, we get a natural log, right? So that ends up becoming natural log of the following. A over A naught, where recall A is my concentration at any time and A naught is my initial concentration. And then now over on this side, that just simply ends up equaling negative KT. Okay. And so there's several ways that we could deal with this equation. So one, we could take E of both sides. And when we do that, we end up with the following. So A over A naught equals E to the negative KT. And you could see we could do that with relative concentration, right, with the A over A naught. Or I could expand that as A equals A naught E to the negative KT. And then now you can see we get that lovely exponential decay. On the other hand, if we were to keep this in this natural log form and expand that out as the following, natural log of A, and I'm going to do just a little bit of algebra here, so that's going to end up being negative KT plus the natural log of A naught. You can see now we're able to make a straight line out of that, y equals negative mx plus b. And you can see now the slope on this log plot would be equal to our rate constant, okay, if it's log of concentration versus time, right? So now you notice here that the exponential decay constant is going to be equal to the rate constant, right? So that's e to the negative kt. But now what about this product evolution, okay? Well, as it turns out, if we want to consider the stoichiometry here, and again, for this reaction, the way I set this up, this reaction is A goes to B. Then we can recognize the concentration of B at any time is going to be equal to the initial concentration minus whatever the concentration is at any given time. So if we make those substitutions then for the product, or in this case for B, then we would end up with the following. We would end up with that B, our product, equals the initial concentration times 1 minus E to the minus KT. Apologies that expanded over to my graph. So I'm going to bubble those off. So here is my first order reactant decay, and this becomes my first order product evolution. And so notice both have that term e to the minus kt, but now we've just had to do a little bit of algebra to arrive at that expression. And just like we did before, we can see what happens if I vary the rate constant. So here I've got just concentration versus time. A is my reactant, B is my product. And now as I increase the rate constant, you can see the reaction finishes at much earlier times. And you'll also notice, because this is an exponential decay, it never quite hits 0, right? So as it's evolving, right, or I really should say the product never quite hits 1. You know, it's going to take a long time. It's hitting 1.00 there just because of the significant digits. But if I back this off, you can see the same thing. So it's just always going to decay or evolve in this way. If I look at the natural log relationship, and here now I'm only just looking at the reactant in this case, there's my log versus time. So you can see here we get that straight line. So it does look like it's a 0 order reaction, but we got to remember that's the log of the concentration. And I know that says log, but that is supposed to be natural log, right? So that is a natural log. So now, in our first order reactions, I also want us to consider what's known as the time constants. Okay, so, and you might recognize one of those time constants as the half-life. All right, so let's get into that. So if we go back to this expression, natural log of A over A0 equals negative KT. And if we define the half-life as where the concentration of A at any time equals 1/2 of the initial concentration, we can substitute that relationship in, and we get the following. So that becomes the natural log of 1/2 A0 divided by A0, and that equals negative KT 1/2. So you can see the A0 and the A0 will cancel. And then now what I end up with is a natural log of 1/2 equals negative KT 1/2. That's just T sub 1/2, right? Noting that that's the time for the half-life. And now doing an algebraic substitution here, and recognizing that I can absorb that negative sign and flip the division in the natural log, then I get the following. That becomes the natural log of 2 divided by K equals the half-life, right? And so you might notice now if my K here, we didn't talk about that before, but as you might guess, K for a first order reaction has to have units of 1/seconds, right? Because now, as you can see in this half-life equation, if K has got units of 1/seconds, then my time will have units of seconds. Or certainly my rate constant could also just be any 1/time unit. So all first order rate constants will always be 1/time. So a more useful quantity for us in first order reactions is actually called the lifetime. Okay, so let's get into that. Lifetime. And that gets a Greek letter tau. So by definition, the lifetime is the following. When A at any time equals 1/E times A0. And that's roughly 37% of the initial A concentration. So what is significant about that? Well, if we keep playing through this same game here, where now I'm going to plug in that definition for lifetime. So now that becomes 1/E times A0 divided by A0 equals negative K tau. hopefully you can see right away what's going to happen in here. The A naught and the A naught's going to cancel. The negative sign will make that the natural log of E. And as you might guess, the natural log of E is 1. So 1 over K, just 1 over the rate constant, gives me the lifetime. And if we think about how that corresponds on our plot here, right? If we were looking at concentration versus time, and we get these decays right here. So half-life, takes us to 50%. Another half-life would take us to 25%. Another half-life would take us to 12.5%, and on and on and on and on and on. If we think of this as lifetimes, however, 1 lifetime, so that would be tau, gets us about 37%. Okay. 2 lifetimes, 2 tau, so I'm just going to say 2 over K equals 2 lifetimes. So that was about 37% has reacted. 2 lifetimes is about 13% has reacted. And 3 lifetimes, so 3 over K equaling 3 tau, gives us that about 0.05% of the reactant remains. And this is exactly where we get that 95th% confidence interval. Technically, the 95th% confidence interval is 3 standard deviations, which is the same thing as saying 3 kinetic lifetimes. So again, in a first order reaction, lifetime is a little bit more meaningful than half-life, even though we see both being used. Okay. All right, that's all that I'm going to say about first order reactions. I'll see you in the next video.